Good evening, everyone. Thank you for being here. My name is Mallika Iyer. I work for Google. I actually started working on this project when I was working at Pivotal as a cloud architect. So this sort of just carries over because I left Pivotal, joined Google 2 months ago. So there is a lot of Cloud Foundry that you'll see. There is a lot of Google Genomics that you will see, and some BigQuery. So I actually had an interesting situation with my laptop because it wasn't connecting to the projector here. And so the code that I'll show you, there's not a lot of code. And luckily, I'm not doing a live coding demo, otherwise I would have not been able to do that. Anyway, so, right. No.
Okay. You just click here.
All right.
Yeah.
Okay, so the challenges that come with not using my own machine. All right, so for the next 30 minutes or so, I will share with you what I've learned. I worked with a lot of customers while at Pivotal, in my past life, and while at Google. And I just want to share over the next 30 minutes my experience working with large-scale organizations who are doing one of various things, right? They have started on what is, you must have heard this buzzword a lot, cloud native, cloud native. So they're either in the process of starting their journey, embracing the cloud, moving their app architectures to the cloud, moving their data stores over to the cloud, or they're somewhere along that transformative process. So over the next couple of minutes, I'll talk about, what I started out with as a baseline architecture, how I evolved over it to run applications that are built for very large, very unpredictable user loads. I'm talking about petabytes and beyond that, running all of that at cloud scale. And the overall goal is it has to be resilient, it has to be reliable. So while architecting for failure. And just wanted to clarify a couple of things because cloud native, it's such an overloaded word. So when I say cloud native from an application standpoint, I'm talking about cloud native applications that conform to a framework or a contract, and it's designed to behave in a predictable way to maximize HA, to maximize resilience, and it's container driven, highly automated, does auto scaling, can self-heal itself, and so on. And cloud native data is a little bit different, right? So when I talk about that, what I really mean is that I want to store it, I want to structure it in a way that it is flexible. So if I want to be able to scale it at a moment's notice, I'm able to do that. I'm not stuck in infrastructure land where I'm trying to size for capacity. So primarily, this is what I'm going to focus on. So some of the challenges that I keep coming across when I talk to customers who are going through this is the first thing that I have seen is, from a data standpoint, either they're maintaining their own data farms, server farms, they have a mishmash of data presence, some in silos, some in the cloud, a little bit in the cloud, and everybody has a slightly unique challenge. So the other problem when you have this kind of a situation is how do you scale? How do you scale really, really fast at a moment's notice for unpredictable workloads? The third problem is when you're architecting in this kind of scenario, there is also the application delivery to think about, and I want an architecture that lends itself to continuous delivery. If I want to push code out multiple times a day, to push features out multiple times a month, I want to be able to do that seamlessly. And lastly, I want, a resilient infrastructure for my application. I want to be able to do the same thing for my data. Basically, my goal is I don't want to I want to future-proof my infrastructure. I don't want to work for my infrastructure. I want it to work for me, and I want to just focus on the actual code, the actual meat of my business, and the thing that's actually going to provide value to my customers, because everything on the infrastructure side, they're not going to see it. It's all behind, but it could really, really affect how your application is used by customers and your audience, right? So the challenge is to create best-of-breed, resilient, a future-proof application architecture, as well as a data analytics architecture that's impervious to scale. So where I started. So this was an experiment that I conducted based on all the things that I keep hearing when I talk to people who are in various parts of this journey, right? So for the purposes for this experiment, I needed a very, very large data set. And there are not that many out there. I mean, you would think about, you talk about, or you hear big data a lot, but there is not that much big data out there. So the first challenge was I wanted a very large data set. And I'm thinking of literally petabytes of data, even beyond that, and something that grows at cloud scale, while not having to deal with being in the business of, maintaining my own infrastructure. I don't want to do that. I want it to be completely serverless. I want it to be able to scale. I want it to be able to handle advanced query analytics, and I'll tell you why in a moment. And, most importantly, again, serverless. I just want to start using the technology. I don't want to set anything up. And natively, I wanted something that had HA, that had global availability, and so on. Basically, the building blocks of what does resilience and reliability in the cloud mean. So So as I tried to, I started looking online. I was trying to look at good data sets that I can use for the purposes of my experiment. And I just got the idea for the data source very randomly. So I have 3 dogs, and and they play with each other constantly. 2 of them are German Shepherds or Alsatians. One of them is a rescue. She's a mix. And it was interesting to me that, my rescue dog, she was actually behaving or almost mirroring the behaviors of my 2 shepherds. And if any of you out here have dogs, you would know that the behavior of a dog is very specific to the breed of the dog themselves. So I just wondered, wouldn't it be great if I can find out her history, find out if she somehow has some sort of German Shepherd genes in her and somehow correlated to other DNA. And basically just like that, I started looking into genomes, and I found some very, very interesting things. So I used one of the publicly available genome data sets. And the interesting thing about genomic data is that if you think about a single human being, one human genome literally has, from a storage perspective, from how much data you need to analyze, it's about 100 gigabytes of data. So the interesting thing is 99.9% of that is the same. There is only a 0.1% that makes me different from somebody else. But the challenge is that in order to find that variance, in order to find the 0.1%, I have to actually analyze everything. So you can see how this can become, an interesting problem really, really fast, because if you just think about, I was thinking about the population of Antwerp, and that itself would literally be it would translate into 52,000 terabytes of data, or 52 petabytes of information roughly. So as I got my data source, my next challenge was I wanted to be able to store this in a meaningful way. So what does that actually mean? In my case, I wanted to be able to store massive data sets. Every time I add, one person's genome, that's literally 100 gigabytes. So I wanted to be able to do extremely fast query processing. So this can differ based on your use case, right? But if I'm storing, 50 petabytes of data, I don't want to start the query and come back after weeks in order to get the information. I want it to be fast. I want want it to be within seconds or minutes. And of course, in order to do all this, I don't want to be in the business of figuring out storage. I don't want to manage my storage. It has to come fully managed for me. So I'm looking at a serverless service model by default. And again, resiliency and reliability means it has to be globally available. It has to be highly available. And in order to do any sort of meaningful query analysis, complex query analysis, variance analysis, and such, it has to support complex query patterns. So basically, I ended up finding Google Genomics. And remember, I sort of ended up in this Google land while I was still at Pivotal. So this whole field completely fascinated me, mainly because it hit all the check marks for my experiment, because I wanted to be able to store, process, and explore the data without writing the tooling. And Genomics API exposes a lot of endpoints that allow me to do this and just let me focus on the code. I don't have to worry about the tooling. And behind the scenes, it actually uses BigQuery in real time. BigQuery is a Google Cloud data product. It uses it to do the data processing and data analysis. And this was amazing because I started digging into BigQuery a little bit more, and I found out that it was perfect because it was literally built to process trillions of lines of logs, and we're talking about interactive speed. So one of the examples that if you just Google it, you'll find this, that basically there is an example that queries over 100 billion rows, that is roughly around 10 terabytes of data. It's basically a lot of Wikipedia data, and it comes back with the analysis in under 30 seconds, which is kind of amazing. So I zeroed in on this part for my data, and then obviously everything was serverless. I didn't have to spin up anything. I just created an account and started using it. So my next challenge was, if I were thinking in a real life kind of a situation, I would need to have application infrastructure as well. So my next challenge was, I wanted to be able to have an application infrastructure that was letting me deploy code several times a month, or as often as it needed, and basically have an intelligent infrastructure that let me auto scale. So I could set thresholds and I could scale it up, or it could do that automatically based on whatever I have defined from how I want to, what is the point at which I want to scale my application up. So another thing that I wanted it to be able to do is it has to be obviously ideal for microservices. It had to be ready to work in container land, so it had to be container ready. And I don't want to be constrained by programming languages either, because what I learned while doing this work with Google Genomics is that I can use Python, I can use R, I can use some other language as well. So I don't want it to be constrained by programming languages. And in a real world scenario, you're going to see, or I'm sure you have probably experienced this in some way or the other. There are groups within your organization. Some of them, or a lot of them, might write Java code. There might be folks who are only focusing on writing services in Go. There is basically a mishmash in every organization. So I wanted it to be future-proof from that point of view as well. And the most important thing, I wanted to be able to connect to any data source from anywhere to anywhere. So it could be on-prem, it could be in the cloud, it could be on Google Cloud. So it doesn't matter. I wanted to be able to connect to that. So this was actually, and obviously it has to be serverless because that was I don't want to be managing all of this. So again, these are all the application challenges that you will see while you're running anything or architecting to do anything in the cloud. And this was a fairly easy answer for me because I was already working extensively with Pivotal Cloud Foundry. So just for those who may not be familiar with what Cloud Foundry is, it's a platform as a service. It is open source, and it supports multiple clouds. And Pivotal Cloud Foundry, it's an enterprise version of that. So basically, getting back to the actual, weeds of it, it's basically a technology that lets me forget about application infrastructure, lets me forget about what I need to do auto scaling, lets me forget about, how do I have containers interact with each other? Basically, how do I have microservices interact with each other? It's a great choice for a microservice-based architecture paradigm. So I said, so basically now my architecture looked something like this, right? So from a very expanded point of view, I have in a real world use case, and I'll show you exactly what my use case was in just a second. So in a real world use case, you might have users who are, doing web, mobile, application, IoT. You might get data from IT. You might, all of these might be using one or more protocols. So from the left to the right-hand side, you can see that all the requests are going via an API gateway, and you might be using HTTP, MQP, TCP, something else. And then there are clusters of microservices that I have within my application that are handling each one of these requests. So the interesting thing is, so my stack is now running on Google Cloud Platform because it was great, it was easy to use, and everything is running on Pivotal Cloud Foundry. So my biggest challenge here was, I don't want to do direct connections to databases because I might want to, it's just not a clean way to do it. I don't want to expose my IP addresses. I don't want to expose my connections. So I don't want to do a direct connection to any of my databases. So in my case, it looked kind of something like this. Only the genomics part was what I was using, right? So in order to not do that, there is a very interesting concept within the Cloud Foundry world. It's called a service broker, and it can be expanded out if you're using Kubernetes or any other platform also. Basically, what the service broker lets you do is it's a component that is implementing what's called the service broker API. So this is where you will implement 5 endpoints which do a number of things, like advertising a catalog of the service offerings. So for example, within genomics, if I wanted to advertise just what is available, which teams can use it, I might say, okay, this team is allowed to do this, this, and this. This is the functionality that's available, and this is the amount of data that they can store. So this differs based on what you're doing. If it's if it's a MySQL situation, you might define a limit on number of concurrent connections. You might define a limit on how much data you can use. So you can expose all of this just by building a service broker, and then you act on those requests. The service broker lets you do provisioning of a database, of an instance, and obviously the opposite part of that also deprovisioning. And then it also lets you bind or talk to an application instance and unbind and sort of gracefully cut off that connection from an application instance in the same way. So I don't have to use any API keys. I don't have to use IP addresses. I don't have to use SSL. It just use bindings. So I wrote my service broker in Spring Boot for a couple of reasons, mainly because I'm a Java developer, and Spring takes a very opinionated way of writing code in the Spring Boot for the Spring platform. So if I am bootstrapping multiple applications and multiple services for production, it's a great tool to use. And within the Cloud Foundry ecosystem, within Pivotal Cloud Foundry, it actually has great support for Spring Boot. So that was kind of a no-brainer almost. So now, diving into each method itself, this is basically where you will define the exact behavior in code. So with respect to what does it mean when you are having your broker implement the catalog method. So for example, I might want, let's take a simple example with MySQL. I might want a plan that says X number of concurrent connections are available. This is the amount of data that's available. I might have multiple plans based on the teams that I'm building it for. So the next one is it could be a create instance. In my case, I was creating a database, but instance creation basically literally spins up an entire data service for you on top of Pivotal Cloud Foundry as well. So I'm not doing that in my case. I'm only creating a database because I am reaching out to Google Genomics, which is running on GCP, and I am creating an database for my experiment. The binding and the unbinding, that is the create binding and the delete binding methods here, that's where I implemented, or this is where you would go and implement the actual brokering of the connections, injecting the connection details into your application instance, gracefully removing that as well, and delete instance versus delete database. It follows that is basically the opposite of the create instance and create database. So this is what my current architecture looked like. So shrinking it down just for the purposes of my experiment, I have everything written using the service broker, and I'll talk about the Open Service Broker API in a second. But basically, I am no longer trying to reach out to my data source directly, and I'm not doing connections that way. So the Open Service Broker API is really, really cool because what it lets me do is, let's say tomorrow I want to be able to, so if you look further below, if I want to be able to move out everything from the from Pivotal Cloud Foundry over to Google Container Engine, which is basically completely serverless. It runs on Google Cloud Platform, so I can do that basically without rewriting any code, because what I would be doing is simply exposing the endpoints, or simply implementing the endpoints in the open source API, open service broker API, like get catalog, which is the catalog method that I told you about earlier. So what I would end up doing is, without any code rewrites, without any change, I can basically completely port all my microservices, all of my service brokers over to an alternative architecture paradigm like this one over here. So this is really a completely serverless architecture if you think about where your data sources are running. So if you are using everything running on the cloud, then now you are free from actually having to manage anything on-prem, because even if you are spending some time orchestrating it, architecting it to run seamlessly on-prem, it is still time that is going away from actually spending all of that energy and all of that effort on your code. So on the right-hand side, you'll see a couple of common offerings or common areas. So I specifically here have pointed out Google Genomics because that's what I used for my experiment, but you might use a variety of, in any architecture, there are NoSQL databases, there are enterprise data warehouses, analytical data warehouses, key value stores. So there are alternatives if you have not actually explored these. Within the Google ecosystem, for example, I could use Cloud PubSub for messaging. I could use BigQuery for doing analytical data warehouses. And there are a number of products that are available using the Cloud Launcher as well. So it's really cool because I don't have to manage anything. I just focus on actually writing the code for my application. So lastly, so just to sum up everything that I talked about, I started out trying to figure out, is there an elegant way to the solution to the problem of I want to go to cloud native application architecture, or I want to be able to move all of my data to the cloud as well. So it's not an easy problem to solve because there are technical limitations in each organization. There are cultural limitations that you have to kind of bridge as well. But basically, if you think about the problem statement itself, if you want to build a highly available, globally available, resilient architecture for data as well as applications, that is a really hard problem to solve. But one thing that I have found is if you pick the right tool, it really helps a lot. Because in my case, just for the scope of my experiment, I picked a really, really large data set. It was petabytes of data. It could potentially be exabytes of data, depending on how much information I push into BigQuery. So if I had selected the wrong tool, I would have just spent a lot of time trying to optimize it, trying to figure out how to make it run efficiently and so on. And this was great because it just works. The other thing is, going back to the application infrastructure side, if you're building containerized applications, there are multiple options out there. In my experience, I worked with PCF, I worked with Google Container Engine. They're both great options, and GC is truly serverless because it runs on GCP, and you just forget about it. And Pivotal Cloud Foundry is great because you can run it anywhere you want. If you really, really need to run it on-prem, you can. And lastly, again, I would not have been able to actually do this experiment end-to-end and prove it out in a successful way without BigQuery, without something that was able to give me that sort of interactive speed that I needed from an analytical data warehouse that was completely cloud native. Because it's challenging if I go to any other alternative that needs setup. I didn't want to do that. So BigQuery is an excellent choice over there. And since this was, my experiment sort of hinged on genome data, I wanted to share a little bit of a trivia with you that I found out. I found out that the number of, so dogs have about, going back to my original inspiration for this experiment, dogs actually have about 19,000 or so protein coded genomes, not that different from human beings. We have roughly around 20,000 or so, and that kind of blew my mind away. So if anyone's actually interested in exploring this further, whether from a genomic perspective, there actually found out there are a couple of dog genome projects that a bunch of organizations are doing that predict or give you the probability of an autoimmune disorder that might happen in your dog, or blindness or deafness or any other kind of disease. And on the flip side, going back to the tech stack, there is a lot more information about BigQuery, obviously, on the Google website, on the Google Cloud website. So if you, and there's a lot of information about Google Genomics there as well. It is really cool. The API is phenomenal. And if you are interested, I highly recommend that you play with it. And that's one of my dogs up there. Questions? Sure.
When you evaluated at the start of your project, when you evaluated different solutions, were there not competitors but alternatives that you found was not well suited for your needs, or maybe you just had an opportunity to use directly maybe a BigQuery or something like that? In other words, are there any solutions that you ruled out for very specific choices that they made, or because they were language specific, you see, or maybe for another reason?
When the reason why I picked the stack that I picked was, so from a language standpoint, I picked Spring Boot for a couple of reasons. It's mainly because Spring Boot lent itself really well to developing microservices on Pivotal Cloud Foundry. I was, to begin with, I started out with Cloud Foundry because I was most comfortable in that area, and it just lent itself phenomenally to deploying application apps, basically microservice paradigm following apps. I sort of, and while I was actually exploring what can hold a lot of data at cloud scale, I I wasn't working with BigQuery at the time. I sort of explored, went towards that area after rejecting a number of options because several options, and I will not name the products, of course, but several options actually had me, I needed, an account, I needed a license, I needed to set up almost a small server farm. It was just not feasible for me. One of the great things about BigQuery is that I can use it as as my data expands or as my data shrinks. So it scales up or it scales down. So that was perfect for me because at the time I wasn't sure how far I wanted to take the scope of my experiment. Did I really want to push petabytes of data into it? Did I want to go beyond that? So it lent itself really well for that. Google Cloud Platform, it was just really easy to use. I worked with a number of other cloud platform IaaS providers as well. And in my experience over the past couple of years, this has been amazingly easy to use. So if you want to, dig a little deeper into that, I'm happy to talk to you offline and, we can go into it if you're interested. All right, my time's up. So thank you very much.